let's do a presentation here. The title of the presentation is Diagonal Checksum Algorithm Based Fault Tolerance for Parallel Matrix Multiplication. This is outlines. The first part is introduction. In a parallel computer system, there may be thousands of computer nodes connected to an interconnection network. Errors may occur in hardware, software, and network. The parallel computer systems must tolerate these possible errors. There are some ways to achieve fault tolerance, like checkpointing technique, but this technique may be difficult in near future because the overhead is very high. The storing time may greater than mean time between fails in a monster system. Another method is algorithm-based fault tolerance. In this work, we proposed another algorithm-based fault tolerance scheme to detect and correct errors. Next, I will talk about the background of checkpointing technique and algorithm-based fault tolerance. The checkpointing technique, saving a snapshot of the application's state. When fault occurs, the application will restart from the last checkpoint. For example, there are 3 checkpoints in this figure. When a fault occurs here, the application will restart from checkpointing 3. The advantage of checkpointing technique is that it can tolerate fail-stop failure because it saved a snapshot of the application. The disadvantage is that the overhead of generation and the storage of the checkpoint is very high. The algorithm-based fault tolerance technique has low overhead. The algorithm-based fault tolerance was first proposed in 1984. In this presentation, we call the first algorithm-based fault tolerance scheme as ordinary ABFT. The ABFT can be applied to matrix operations like matrix multiplication. Give a matrix a redundant column vector or row vector can be added to the matrix. The column vector is called column checksum, and the row vector is called row checksum. In these figures, the green blocks indicate the checksum. A matrix is called column checksum matrix if it only has a column checksum. A matrix is called row column checksum if it only has row checksum. If a matrix both has column checksum and row checksum, we call the matrix as full checksum matrix. As the formula shows, a column checksum matrix multiply a row checksum matrix is a full checksum matrix. The ordinary ABFT can detect and correct one error of a full checksum matrix. The red block indicates the error elements. We compare the sum of elements in each row and each column to corresponding column checksum and row checksum. The location of the error can be determined. The sum of elements in same row with an error not equal to the row elements. The sum of elements in same column with an error is not equal to the corresponding column checksum. After determining the location of the error can be corrected by the row checksum or column checksum. The overhead of ABFT is low and it can tolerate soft error. Next, I will talk about the diagonal checksum ABFT. The limitation of the ordinary ABFT is that it can only detect and correct one error. More than one error cannot be detected and corrected. For example, there are two errors in a matrix. In these figures, the red blocks indicate error elements. The pink blocks indicate the possible error elements but correct. We cannot determine the errors in red blocks or pink blocks. The errors can be detected but cannot be corrected. So we proposed a new algorithm-based tolerance scheme named the diagonal checksum ABFT to detect and correct two errors. This figure shows the diagonal checksum ABFT. Similar to ordinary ABFT, the diagonal checksum ABFT also aids the column checksum and the row checksum. In addition, diagonal checksum ABFT aids two additional diagonal checksum. The diagonal checksum is the sum of the elements along the diagonal line. Depending on the diagonal direction, we can get two types of the checksum: left diagonal checksum and right diagonal checksum. Algorithm 1 shows how to detect and correct two errors. First, we check the sum of elements in each row and each column according to the corresponding checksum. Then we mark inconsistent rows and inconsistent columns. Second, we check the sum of elements along the diagonal according to the corresponding diagonal checksum. Then mark the inconsistent diagonal lines. By the intersection of marked rows, columns, and the diagonal lines, we can determine the location of errors. If there are more than two marked rows, columns, or diagonal lines, this means that more than two errors have occurred. The algorithm will be ended. Finally, we can correct the errors by row checksum, column checksum, or diagonal checksum. Here is an example of diagonal ABFT detecting and correcting two errors in a matrix. The red blocks indicate the elements where the error occurred. Pink blocks indicate the elements that could be wrong but are actually correct. There are two rows and two columns are marked inconsistent. Error occurring in the red blocks or pink blocks can lead to the same marked inconsistent rows and columns. With row checksum and column checksum, we cannot determine the location of the errors. In order to determine the location of errors, we should check the sum of elements along the diagonal line. Since there is no error in the elements of the pink blocks, the sum of elements along the diagonal sum of the diagonal elements through the pink blocks is equal to the corresponding diagonal checksum. The diagonal check line will not be marked. In this case, there are three diagonal lines through the pink blocks, and the corresponding diagonal checksum will not be marked. So we can rule out the case that errors appearing in the pink blocks. We can determine the errors appearing in the red blocks. After we know the location of the errors, we can correct the errors by row checksum, column checksum, or diagonal checksum. The first part is performance evaluation. we implement the matrix multiplication by parallel. The Scalable universal matrix multiplication algorithm was implemented. Here is an example of parallel matrix multiplication with 16 processors. We arrange the 16 processors in 4x4 grid. Each processor has a submatrix of ordinary matrix or original matrix, and each processor broadcasts its submatrix elements to the processor in the same row or column. The multiplication operation was done in each processor by the submatrix. For each processor's matrix, the row checksum, column checksum, and diagonal checksum will be added to the submatrix. The fault model also should be discussed. We assume only soft errors occur. This means errors cannot damage the system but will lead a wrong result. We assume the interconnection network is unreliable. We do not use the forwarding error correction to correct the transmission errors. Without the overhead of the forwarding error correction, the latency is reduced and the bit error rate becomes larger. We assume the errors occur during message transmission. The figure shows an interconnection network with 16 nodes. The source node sent a message 000 to destination node, but a bit flip occurs during transmission. The message was changed to 0010 because the diagonal ABFT can detect and correct two errors. If there are more than two errors, message should be retransmitted. We simulate the evaluation on the simulator SimGrid. The computing power of each host node is 100 gigaflops. The switch delay is 100 nanoseconds. The bandwidth between the switch and the host node is 100 gigabps. The topology of the network is 40 cores. This figure shows the execution time of matrix multiplication under different matrix sizes when the bit error rate is 10 to the power of minus 12. The number of computer nodes is 64. The ordinary ABFT increased by up to 3.5% the execution time. The diagonal checksum ABFT method further increased by up to only 2.7% the execution time compared to the ordinary ABFT method. This result shows the overhead of diagonal ABFT is very low, under a low bit error rate. This figure shows the execution time of matrix multiplication under different computer nodes when the bit error rate is 10 to the power of minus 12. The matrix size is 256 by 256. The result also shows the overhead of diagonal ABFT is very low. This figure shows the execution time of matrix multiplication under different bit error rate. The matrix size is 1024 by 1024. The number of computer nodes is 64. When bit error rate is lower than 10 to the power of minus 7, the execution time of diagonal checksum ABFT methods increased at most only 4.9% compared to the ordinary ABFT method. When bit error rate is higher than 10 to the power of minus 7, the execution time of ordinary ABFT starts to become larger than that of the diagonal checksum ABFT method. This figure shows the success rate of transmission under different bit error rate. If all errors are detected and corrected without retransmission, we count each ABFT method as a success. Matrix size is 1024 by 1024. The number of computer nodes is 64. When bit error rate is less than 10 to the power of -8, the ordinary ABFT and the diagonal checksum ABFT method always achieve almost 100% of the success rate. When bit error rate is 10 to the power of -7, the success rate of the ordinary ABFT method becomes 65%. In contrast, the diagonal checksum ABFT method has 93% success rate. This result shows the diagonal ABFT works better than ordinary ABFT under low bit error rate like 10 to the power of -7 bit error rate. The last part is conclusion. We propose a diagonal checksum ABFT method for tolerating two errors by adding additional two diagonal checksums to an original matrix. The overhead of diagonal checksum ABFT method is similar to ordinary ABFT method. It works well even when an interconnection network reaches 10 to the power of -7 bit error rate. Finally, I will introduce a related work of ABFT to correct multiple errors. A weighted checksum ABFT method was proposed. D-weighted checksum can be added to a matrix sum. If D is 2, one error can be detected and corrected by this process. If D is 5, 2 errors can be corrected, but the error detection and correction method is complicated than our diagonal checksum method. Our diagonal checksum method is easy implemented. Thank you very much. That's my presentation.